1.2.1 The periodic table. You've got to know how in the modern periodic table, now the one that you look at, especially the one you get at your GCSE or the one you get in front of you for your mock exams, the elements are arranged in atomic number order. We now know that every different element has a different number of protons, so we can arrange them in that order. Remember from the previous periodic table, for Mendeleev's periodic table and before Mendeleev, that they arranged it in the information they knew. So they went for atomic mass order. But you've got to remember that the elements in the periodic table are arranged in atomic number order. Now, when we're looking for patterns and trends, we've now discovered in our modern periodic table that elements with similar properties are in the same column. Now, we call them groups. Elements in the same group have similar chemical properties because they have the same number of outer shell electrons. Do you remember that phrase? Outer shell electrons. So for instance, elements in group 1 all have one electron in their outer shell. So lithium is electron arrangement 2.1, sodium 2.8.1, potassium 2.8.8.1. They all have one outer shell electron, so they share similar chemical properties. Likewise, the elements in group 7, the halogens, they have similar number of outer shell electrons. Fluorine 2.7, chlorine 2.8.7. After that, it gets a little bit more complicated in terms of the number in the outer shell, but you just need to remember that all of the elements in group 7 need to gain one electron to have a full outer shell, so therefore they have similar chemical properties. Then if we consider group 0, the noble gases, we've got to look at them as a rare breed of elements. They can exist on their own. They don't need to form bonds with other atoms to be stable. That's because they have a stable electron arrangement. In other words, the outer shell is full. That means they don't have to form a chemical bond to become stable. So for instance, helium 2.0, neon 2.8.0, argon 2.8.8.0. They all have a stable electron arrangement, SEA, stable electron arrangement. I once went out with a group of noble gases and someone came over and picked on them. And I was like, why didn't you say anything? And they looked at each other and said, we're noble gases, we don't react. We will go on and look at group 1, group 7 and group 0 in more detail. So just for now, make sure you've got the point. The elements with similar number of outer shell electrons will be in the same group because they have similar chemical properties. 1.2.2 Development of the periodic table. So take yourself back before protons, neutrons and electrons had been discovered. The only information they had was the atomic mass. The previous periodic table was arranged where the elements were in order of their atomic mass. Now there were problems that weren't their fault, to be fair, with the early periodic table. The table was incomplete. And because it was incomplete, whatever order they put it in, there were going to be some elements that were in the wrong groups based on their chemical properties. So you had groups of scientists that said we must stick to the atomic weight. Then you had other groups of scientists were saying, but these elements go together, so we'll put them next to each other or above each other and below each other in the table. Now Mendeleev was the pioneer behind our modern periodic table. So he left gaps because he was convinced there would be undiscovered elements that would be discovered later. The other thing he did was he rearranged the order so that the reactivity in the groups matched, even if the relative atomic mass didn't. Two examples here to consider. If you look at tellurium and iodine in the modern periodic table, they're in the wrong order based on their atomic mass. They should be the other way around. But if they were, then iodine wouldn't be in the same group as fluorine, chlorine, bromine. And we know that iodine is a halogen. It has the same chemical properties and follows the same trends as the other elements in group 7. The other ones, if you look at, are in the wrong order, are argon and potassium. Now argon is a noble gas, it's unreactive, and potassium couldn't be any more different from argon. It's a very, very, very reactive metal. So what he did is he put potassium in the same group as lithium and sodium, and he put argon in the same group as helium and neon. So as I've said, elements were discovered that matched Mendeleev's predictions. And now we've got a really better understanding of the atoms and the order of the periodic table. And actually, our knowledge of isotopes can explain why some atoms were in the wrong order based on their atomic mass that they didn't know about back then. And remember the two differences that Mendeleev made. First of all, he left gaps for undiscovered elements, which he predicted the properties of. And secondly, he wasn't afraid to change the order so that elements with the same properties were in the same group. 1.2.3 Metals and non-metals. 1.2.3 Metals and non-metals. So you've probably done an experiment in class where you've looked at the properties of metals and non-metals. And my class, remember, lust after McDonald's. McDonald's. So lust stands for lustrous, which means that the metals are shiny. Secondly, we've got this idea of M. It means that metals are malleable, it means they can be bent into shape easily. The C stands for the conductivity of metals because they have delocalized electrons. Then the D stands for ductile, which means they can be stretched into wires easily without breaking. And the S stands for sonorous, which means when you hit them, they make a ringing noise because all the atoms vibrate at the same frequency, making that beautiful sonorous ringing noise. The properties of non-metals are like this. They're brittle, which means they don't bend easily. They break when a force is applied to them. They insulate. They're not good thermal conductors because they don't have delocalized electrons that can move through the structure. And they don't have shiny surfaces normally. They are dull. So brittle, insulators and dull. Now in terms of the chemistry of metals and non-metals, they are different. Metals react to form positive ions by losing electrons. The opposite is true for non-metals. Non-metals gain electrons and form negative ions. So they form negative ions by gaining electrons to have a full outer shell. If you look at the periodic table, you can see where the metals and non-metals are. Metals are at the left-hand side of the periodic table. In fact, the most reactive metals are in column 1 at the far left of the periodic table. Then group 2. Then there's a middle group called transition metals. If you look at the top right-hand corner of the periodic table, that's where you find the non-metals. So if you have a look on the little list there, you've got helium, carbon, nitrogen, oxygen, fluorine, neon, silicon, phosphorus, sulfur, chlorine, argon, cerium, bromine, krypton, iodine, xenon and radon. Those are non-metals. So if you want to find the non-metals, you need to look at the top right-hand corner of the periodic table. And what you'll notice from the list that you can see there is there aren't as many non-metals as there are metals. Make sure you can identify in the periodic table where the metals are and where the non-metals are. And make sure you can understand the difference in terms of the chemistry, where metals lose electrons to form positive ions and non-metals gain electrons to form negative ions. 1.2.4, Group 0, the noble gases. So you need to know group 0, the noble gases, they are unreactive. The reason they're unreactive is they don't easily form ions or compounds. So they don't react. The reason they don't react is they have an SEA, a stable electron arrangement. That means they've got a full outer shell. They don't need to gain or lose electrons to become stable. So when you consider the electron arrangement for helium, He, it's 2.0. When you consider it for neon, it's got 10 electrons, so its electron arrangement is 2.8.0. And when you consider it for argon with 18 electrons, it's 2.8.8.0. They all have 0 electrons in their outer shell, or you could say they've got a full outer shell. Now in terms of the properties, as you go down group 0, the noble gases, what you find is the boiling point increases. So that the temperature at which they boil gets higher. The reason for that is when the relative atomic mass increases, there's bigger forces between the atoms that need separating. When we're considering Unit 7, the boiling point of hydrocarbons, you'll know that as the chain length increases, the boiling point increases because of the relative atomic mass increases, and there are stronger or more intermolecular forces holding the molecules together. So therefore more energy is required to separate the molecules. That's the same with the noble gases. As the relative atomic mass increases, the intermolecular forces increase. Make sure you know why group 0 are unreactive and why the boiling point increases as you go down the group. 1.2.5, the alkali metals. All elements in the same group have the same number of outer shell electrons. So all elements in group 1 have one outer shell electron which they lose to form a +1 ion. So let's look at the electronic structures. Lithium 2.1, sodium 2.8.1, potassium 2.8.8.1. All of them have one outer shell electron. Because they only need to lose one outer shell electron to form a stable ion, they react really violently or really well. 3 reactions you need to know about. First of all, they react with oxygen in an oxidation reaction. So for instance, lithium. Lithium will react with oxygen to make lithium oxide. Now, a couple of things to note about this equation. 1, the formula of lithium oxide is Li2O. That's because the lithium has a +1 ion and the oxide ion is -2. So you need 2 lithium ions for every 1 oxide ion. So when it comes to balancing it, the first thing I would do is this. I would say there's 2 oxygen atoms on the left hand side, but there's only 1 oxygen on the right hand side. I'm going to have to double that, otherwise I can't balance it easily. So I'm going to put a 2 in front of the lithium oxide. Now I've got 4 atoms of lithium on the right hand side and I've only got 1 on the left hand side. So what I'm going to have to do is put a 4 in front of the lithium. And if you do that, it's balanced. 4Li plus O2 goes to 2Li2O. You need to know that group 1 alkali metals will react with halogens, group 7. And this is a really good reaction because the sodium atom needs to lose 1 electron and the chloride ion needs to gain 1 electron. Therefore, the formula of sodium chloride is NaCl. Now we've got 2 atoms of chlorine on the left hand side but only 1 on the right hand side. So we're going to have to put a big 2 in front of the NaCl. Now we've got 2 atoms of sodium on the right hand side, so I'm going to need to put a 2 in front of sodium at the left hand side. Thirdly, you need to know that group 1 alkali metals react with water to make a hydroxide and they give off hydrogen gas. Now if you have a little look at this reaction, you'll notice that each water molecule loses a hydrogen atom. So for instance, H2O goes to OH and H. But actually it says H2 at the end, so I'm going to need 2 water molecules. If I've got 2 water molecules, I'm also going to need 2 potassium atoms. So I'm going to have to put a 2 there. And if I've got 2 potassium atoms and 2 water molecules, I'm going to make 2 lots or 2 moles of potassium hydroxide, KOH. So the balance is 2K, 2H2O produces 2KOH and H2. Finally, you need to know the reactivity of the elements in group 1 increases as you go down the group. Now the way I remember this is DIES. The first reason is this: the distance from the nucleus, which is positive, to the outer shell increases as you go down the group. So there's a bigger distance. The other thing is this: there's inner electron shielding. So the IES stands for inner electron shielding, which stops the outer electrons being attracted to the nucleus. What this means is that it's easier to lose an outer shell electron. Therefore, as you go down the group 1 metals get more reactive. Make sure you can explain the reactivity of group 1 metals before you move on. 1.2.6, group 7, the halogens. So you need to know all elements in group 7 have 7 electrons in their outer shell. They need to gain 1 electron to form a stable electron arrangement. Now halogens are non-metals and exist as molecules, as a pair of atoms. Now they form ionic bonds when they react with metal atoms. So for instance, sodium and chlorine react together to make sodium chloride, which is an ionic compound. Halogens will react with non-metals to form molecules, covalent molecules, where they share electrons. So when you look at covalent bonding, you'll know that a covalent bond is a shared pair of electrons. So for instance, hydrogen and chlorine will share an electron each to make hydrogen chloride, HCl, which is a gas at room temperature. Just like with the noble gases, the boiling point increases as you go down the group. It increases because the relative atomic mass of the molecule increases. And you'll know when you look at Unit 7 with hydrocarbons and fractional distillation, as the molecule gets bigger, the boiling point increases because there's bigger intermolecular forces that require separating. Consider group 1 elements. Group 1 elements get more reactive as you go down the group. Well, group 7 elements get less reactive down the group. The reactivity decreases as you go down the group. The acronym's the same, DIES. The reason they get less reactive is the distance from the positive nucleus to the outer shell gets further as you go down the group. And there's more inner electron shielding. That means it's harder to gain an electron to form a negative ion. That is why the reactivity decreases. When you consider then the relative reactivity of the halogens, you can compete them against each other. The competition is called a displacement reaction. So when we consider the reactivity of the halogens, chlorine in this example is more reactive than bromine. So chlorine atoms will kick out the bromide ions, forming bromine. The chlorine atoms will become chloride ions. So we'll go from sodium bromide and chlorine, where chlorine is a pale green colour in solution, to sodium chloride and bromine, which is an orangey brown colour in solution. So when we did this reaction, we know it had taken place because there'd be a colour change from pale green to orangey brown. In order to balance this equation, we've got to notice that on the left-hand side there's 2 chlorine atoms, Cl2. And on the right-hand side there's 2 bromine atoms, Br2. So what you need to do is put a 2 in front of the NaBr and a 2 in front of the NaCl. So the balancing is 2 NaCl plus Br2 produces 2 NaCl plus Br2. Make sure you know about the reactivity of group 7 before you move on. Make sure you know about the changes in boiling points as you go down group 7. And make sure you understand about the relative reactivity and displacement reactions before you move on.